Ladies and gentlemen, my dear friends, hope you are all feeling great today. Alright, let's walk through adaptive learning rates together. What are they? When you train a model with the basic gradient descent idea, every parameter takes a step using the same learning rate. You can see on the screen that the learning rate is written as alpha, and we usually write it as like a, but it is alpha. Okay. Now this seems simple, but once you start applying it to real problems, it causes a few issues. What are they? Some directions in the loss surface can be steep, others flat, and using the same step size everywhere creates a trouble. So let's talk about why this becomes a problem and what adaptive methods try to fix. Okay, now take a look at the left box on this part. And when gradients are large in one direction and small in another, the model behaves awkwardly. If the learning rate is too large, the update bounces around the steep walls, and if it is too small, the model crawls along the flat direction forever. So you end up with this odd situation where one parameter wants a tiny step and another wants a much bigger one. Using one shared alpha for everyone makes it to satisfy both. And on the right side, you can see something related but coming from another angle. In fields like natural language processing or recommendation models, some features appear rarely. Those rare features hardly get updated, so they need stronger steps. But frequent features already get updated a lot, so they need smaller steps to stay stable. A single global learning rate can't balance these competing needs. That's one reason researchers started thinking, why could not each parameter have its own learning rate? And that brings us to the idea of per parameter learning rates. The next section here explains that adaptive methods assign a learning rate to each parameter based on its past gradients. So, if a parameter has seen large gradients a lot, we reduce its step size. If it rarely gets updates, we give it a larger effective learning rate. It's a simple idea. Let the data decide how aggressively each parameter should move. And look at the contour plot shown next, where the function is written like that, you know, f of x comma y equals x squared plus 10y squared. So this function stretches more in the y direction, which means the slope changes faster vertically than horizontally. That's why the path curves the way it does. Regular gradient descent struggles because it must tiptoe along the steep direction while trying to move more freely in the flat one. Okay, now we enter ADGRAD. ADGRAD stands for Adaptive Gradient, and it was proposed in 2011 by Ducci and colleagues, and it was one of the first successful methods that assigned a different learning rate to each parameter. ADGRAD builds a running total of squared gradients. This allows it to scale the learning rate based on how active a parameter has been throughout training. So the formula you see is that, what is that? G sub tii equals G sub t minus 1 ii plus G sub ti squared. So here G is a diagonal matrix storing the sum of squared gradients for each parameter up to step t. Then the update becomes that, what is that? Theta sub t plus 1i equals theta sub ti minus eta times G sub ti divided by square root of G sub tii plus epsilon. So you are basically dividing the gradient by the accumulated square roots. So repeated weak gradients shrink the learning rate automatically. Okay, and on the left side here, explanation box that follows, you see the logic. Large accumulated gradients reduce the denominator, lowering the effective learning rate. Small accumulated gradients keep the denominator small, rising the effective learning rate. So parameters that have been busy slow down and parameters that have not been moving much speed. But there is a catch. Since g keeps adding square gradients, it only grows. It never decreases. That means the effective learning rate keeps shrinking until it becomes tiny. This causes the so-called dying learning rate situation. Your optimizer moves well in the beginning, then it slows down so much that it partially freezes before reaching the minimum. And when you check the A-degrade trajectory on the contour plot below, you can see it starts off pretty direct. It avoids the bouncing problem because it quickly reduces the learning rate in the steep direction. And then it fizzles out early because the step size becomes too small. So yes, it behaves better than vanilla gradient descent, but it still gets stuck. Okay, that's it. And here, let's switch to RMS-Prop. This method was proposed by Geoffrey Hinton in one of these lectures, and RMS-Prop takes the original idea of A-degrade but changes how the learning rate adjusts. Instead of summing square gradients forever, RMS-Prop uses an exponential moving average. That means it remembers recent gradients strongly and older gradients fade away. So the learning rates don't collapse permanently. By the way, it is rule mean square propagation. Okay. And the equation you see here, what is that? Let's read. E of g squared at t equals gamma times E of g squared at t minus 1 plus 1 minus gamma times g sub t squared. Then the update becomes here. And what is that? Theta sub t plus 1 equals theta sub t minus eta times g sub t divided by square root of E of g squared at t plus epsilon. Because of this averaging, past gradients slowly leak out, avoiding the permanent collapse that harmed A-degrade. Okay, and when you look at the RMS-Prop counter figure, you can see how the path bends smoothly. It still reduces the learning rate in steep directions, but because the average doesn't grow forever, the optimizer keeps enough velocity to reach the minimum. And in practice, RMS-Prop became particularly popular for models like RNNs, since their gradients can vary widely depending on the context. Okay, and let's continue. And then comes ADAM. ADAM stands for Adaptive Movement Estimation, introduced by Kingma and Ba. So it combines ideas from momentum and RMS-Prop. Momentum gives you a running average of past gradients, which we write as like that. M sub t equals beta 1 times M sub t minus 1 plus 1 minus beta 1 times G sub t. This tracks the direction of provides a smoother path. Then Adam also keeps a second moving average of square gradients written like that. And what is that? V sub t equals beta 2 times V sub t minus 1 plus 1 minus beta 2 times G sub t squared. So the first movement mt handles direction, and the second movement BT handles magnitude scaling. Okay, and but only in training, these averages are biased towards zero because they start empty, and that's why Adam adds a correction step. And you see these formulas: m hat t equals m sub t divided by minus beta 1 to 1 to the t, and this v hat t equals v sub t divided by 1 minus beta 2 to the t. And the final update is here. Theta sub t plus 1 equals theta sub t minus eta times m hat divided by square root of v hat t plus epsilon. And this makes Adam stable both at the start and throughout training. So here, when you look at the Adam trajectory in the contour figure, you can see how smooth the path is. It doesn't sink unnecessarily and it doesn't stall too early. Momentum helps it move decisively and the adaptive scaling keeps it under control. That combination is why Adam became default choice for many deep learning tasks. Okay, here, and bias correction, and final page is here. Down in the summary table, you can see how all optimizers compare. And SGD makes simple linear updates, momentum adds velocity, ADGRAD adjusts learning rates per parameter but decays too aggressively, RMS Pro fixes the decay issue with a leaky average, and Adam mixes momentum with RMS Pro ideas and tends to work well across a wide range of models. So when you start a new project, you will often begin with Adam because it's reliable and doesn't force you to tune too many settings. But it is still important to learn what each method does because once you understand how they behave, you can choose the one that makes the most sense for your task. And thank you for listening.